So thank you for the chair for the introduction. Now today I will talk about our research on the distributed function secret sharing and its applications. This is a joint work with Hongwei Li, Menghao, Han Xiaochen, Jiahu, and Dongxiao Liu. So let's start with the background. Our work lies in the field of secure multi-party computation, and the secure multi-party computation has been a powerful tool in protect the user privacy in the currently society. For example, here I give a privacy-preserving model inference to show you how it works. And during this process, the client will submit its private data based on some encryption scheme or the secret sharing scheme to the MPC protocols, while meanwhile the server who holds the model weight will also use the same method to submit its private weight to the protocols. And during the execution of the protocols, the server and the client will interact in multiple rounds and send some intermediate data. And finally, the client will receive its confidential inference result without disclosure to the server. And during this whole process, the main problem, or we call the overhead, is come from the communicate progress. And in the recent years, there is a new crypto primitives called function secret sharing. It is a powerful tool for construct online efficiency MPC tools because it has divided the whole protocol into the two phases. One is called the offline phase, and the other is called the online phase. During the offline phase, the typical function secret sharing scheme requires a dealer to generate the FSS keys, and then it distributes the keys to the parties and the client respectively. At the online stage, the parties only have to use the keys and run the evaluation algorithm. During the online phase, the parties and the server do not need to communicate a lot of data. They only need to interact with the constant complexity of rounds and the only several ring elements to complete this computation process. However, the existing FS scheme is not sufficient. We mainly face two challenges here. The first challenge is that traditional FSS scheme requires a dealer that during the offline phase, it has to generate the keys for the two parties, which is unrealistic and weakens the security guarantees. And the second challenge is that there are several dealerless FSS implementations proposed before, but these solutions have limited practicality because they cannot unable to support both arithmetic input and output simultaneously, and they may face potential performance bottleneck incurred by the large bit length of the input. So in this work, we have proposed the dealerless FSS scheme, including the arithmetic DPF and DCF functions. Based on this, we built several FSS-based building blocks and complex function evaluation protocols. And our open source implementation demonstrates that the solution we proposed achieve significant communication improvement and runtime improvement. So let's start with the technical part. And to construct a dealerless FS scheme, we have to recall that how the keys was generated when there is a dealer. To generate the key, the dealer should firstly construct a GGM tree. It is a binary tree and which was completely defined by its root node. And we have put an example of each node on the middle of the slides, and we will format this node into a label and a 1-bit control bit. And we will use the last control bit as the DPF function. Oh, I want to introduce the DPF first. The DPF is a is called the distributed point function. It will, as you see, there is a binary tree, and in each DPF, we have a special point marked in the red color. And during the DPF, there is a way along the root node to the red node, which we call it a special path. And the final control bit of the target node, it will become the secret shares of 1, and otherwise there will be secret shares of 0. So when we have to to generate a DPF key when there is a dealer, we first call the dealer to construct a random GGM-style binary tree. Okay, but the last control bit will be pseudo-random, and we have to use the correction words to correct it to maintain the DPF environment. The DPF environment requires that all the nodes on the path will have the control bit to be 1, and all the off-path nodes have to be the control bit of 0. So the DPF key components consist of a root seed to determine the full random tree, and the correction words for each level to correct the last control bit to 1 to maintain the DPF environment. And so when we have to construct the dealerless DPF, we face the first problem is how to traversing the GGM tree, because there is no dealer and we do not know the red marked special path. So we have to use the two-party computation protocols to traverse the GGM tree. And the problem is that currently we do not know which is the path to the target node. And we construct this protocol based on the observation that although we do not know is the exact path, but all the off-path nodes are 0. So if we sum the off-path nodes and together, they will be the same result as what we have already know the path. And finally, we can use a secure selection protocol to achieve this, to get the correct result, even there is no such knowledge of the special path. And the second is to support the arithmetic output. As I have stated before, if we only use the last bit to define the final output, it will be only a one-bit protocol, and this is what we call the Boolean output. So if we want to make the output into a general ring, or we call the arithmetic output, we have to compute the extra data or the extra correction word for it. This is for the complete details. We refer the reader to read the FSS scheme proposed in the Eurocrypt by Boiler, and here we only talk the most crucial part of it. During this calculation, we have to complete the computation of this equation, and this equation requires that we have the knowledge of the T1, which was the control bit held by party 1. But this is a distributed two-party computation protocol, and during the protocol, it is hard to compute the powers of -1 based on the T1's part. So we have to. So our solution is that because the T1 is only a 1-bit value, as T1 equals 0 or 1, there are only these two conditions, and we can turn this problem into determining which part holds the larger value. If the part holds the larger value, we can infer that they hold the big value of 1. So when we do not know the exact path or the exact red marked path, we can only sum up them together and use our efficient comparison protocol. And we find that to complete the comparison, we only have to extract the last 2 bits, and we categorize the comparison into the following conditions, and finalize the computation with only AND gate by the secure AND protocol. And now for the DCF, or the distributed comparison protocol, it is based on the DPF, and we can simply use it via the generic 2PC protocols to compute more correction words with the 2PC functionalities. However, we find that this can be further optimized, that because the parties can after they have computed VCW, we can locally compute the following equation, as we have to only keep the right side or the left side of the part, and the above equation equals to this one. This is exactly what we need to calculate the V alpha. So we just to locally subtract the previous, multiplex the output to get what we need in the purple ones. So the next is the basic building blocks. The first is the equality test. The equality test is very simple due to its name and with its offset version. And here we just use one DPF invocation as the k plus r, where the r is a random mask. And for the comparison, the comparison we cannot use the same due to the integer comparison protocols. During this process, the k plus r may be overflow and lead to incorrect results. More particularly, there are no conditions where one is overflow and another is non-overflow. During the two cases, we have different correct intervals. So our solution is to check if the k is bigger than k plus r as the offline stage, and then it's our more useful building blocks for truncate and reduce and interval containment to change the value into a smaller ring, and the digital decomposition protocol to decompose a bigger value into several score segments with our DPF and DCF implementations. So let's go to the final part of the application in the scientific computing. First, we propose two efficient functionalities for the lookup table. Okay, I will finish it quick. And for the lookup table and the polynomial approximation by the DPF and DCF building blocks. And during the approximation, we have to calculate this under truncated bits, so that we do not have to face the large bit performance caused by the input. And finally is the trigonometric evaluation. Here we use the periodic properties and the sum-to-product identity to complete the computation. And this is our evaluation result. For the dealerless DPF and DCF, we can generate the key for the few seconds. And for the trigonometric evaluation, the experiment demonstrates that we have much improvements compared to the prior work. And finally, we have implemented into two case studies and to show that our efficiency for the whole solution. And that's all for the presentation. And I'm ready to take any questions.
Yeah, thank you very much. The speaker will be happy to answer questions, but please offline because we're out of time. But I'm sure he will be happy to help you later on. I'm sorry about that. Okay, thank you very much.
Okay.